We've talked a little bit about modal diagonal form. I want to show you how to take a system and put it in modal diagonal form. But also I want to show a little bit of the derivation for why modal diagonal form works. Why is it a useful thing is really important, but how it is that you can know that modal diagonal form is an equivalent representation is also important. So let's take our standard linear time invariant definition of a system. X dot equals ax plus bu, y equals cx, and x at time 0 equals some vector x0. So with this representation, we have our state update equation, x dot, so this is how state changes with respect to time. And then we have our output equation, y equals c times x. And then we have our initial conditions, x of 0 equals x0. So with this system, we have a bunch of pieces that we have to define how they represent, or how they are in the space of real numbers. So x is an n-dimensional vector, so r is n by 1. U is m by 1, or r to the m. And y, in this case, is just nr. So you can have multiple dimensions of y, but I've just got one dimension here for simplicity. And A is an n by n matrix. B is an n by m matrix, because B takes our outputs and converts them into state updates. So it's m for the number of outputs, and m for the number of outputs, and n for the number of states. And C is a 1 by n. Of course, this is because y is just in one dimension. If y was in two dimensions, then C would be an r of 2 by n. So the solution to this equation, the solution x of t to this differential equation is e to the at times our initial condition x0. So e to the at is the state transition matrix, exponential matrix. x0 is our initial condition. So this piece defines the transient response to the initial conditions. And then we have this piece that describes how we respond to new inputs. So again, we use the exponential matrix here, e to the at minus tau times b u of tau d tau. And y we calculate after we calculate x. So the trouble is that e to the at is a pain to compute if it have lots of elements in it that are not equal to 0. So we'd like a less painful way to calculate y of t, especially because y of t is what we care about. We care about making sure that our system is stable. So here's an idea. What if e to the at were easy to calculate because we had some matrix that was diagonal? So I'm going to call this matrix A bar whenever we're talking about a diagonal matrix. So if we have a diagonal matrix A bar, which is also square, then we can calculate e to the A bar t in this way. So this is the same way that we calculate e to the at, it's just that a happens to be diagonal here. So we take si minus a bar, and we invert it, and then we take the inverse Laplace transform of si minus a bar inverse. So for this 3 by 3 example, we end up with the three elements that make the system diagonal, s minus a1 bar, a2 bar, and a3 bar. So we're going to take this matrix, which has only three elements that are non-zero, and they're on the diagonal. And we can look and see what happens when we try to invert a matrix that only has diagonal elements. So I've sort of skipped to the end on this, because you can find this in a matrix textbook, or you can go watch a video about inverting a matrix. But essentially what you get is the determinant, 1 over the determinant. So this is the product of the three diagonal elements. And then along each diagonal element, you still have left in the numerator the product of the pieces, but they leave out the piece that you used to have here. So here we have s minus a minus 1. After we invert it, the same element in the matrix is missing the s minus a1 bar piece. So we're left with s minus a2 bar times s minus a3 bar, where s minus a1 bar used to be. So this is just, again, a product of the fact that we're inverting a diagonal matrix. So what's nice about this is now when we multiply through by the determinant to here, the s minus a bar 2 will cancel with this s minus a bar 2. S minus a bar 3 will cancel with this. So we're left with 1 over s minus a1 bar, where s minus a1 bar used to be. So it's pretty easy to see why this is a convenient way to invert this matrix, because we can inspect si minus a bar. In fact, we can just inspect a bar to see exactly what we're going to be dealing with. So L inverse, the inverse Laplace transform of 1 over s minus a1 bar, 1 over s minus a2 bar, 1 over s minus a3 bar, is e to the a1 bar t, e to the a2 bar t, e to the a3 bar t. So this is a very fast way to compute the inverse Laplace transform, and therefore to compute e to the a bar t. If a bar is diagonal, e to the a bar t is really easy to compute. But that doesn't help us, because we still have e to the at, and e to the at was a pain. So we want to come up with some way to calculate e to the a bar t that will give us the same answer that e to the at gave us. So this is going to take a little bit of an intuitive leap. How can we make that happen? Well, one way that we can make that happen is that we can define a magical matrix P. So we're going to choose P such that we can convert our state x into another state x bar. So P is a magical matrix that will take us to a new land where a bar is diagonal and we can all ride unicorns or something silly, right? So it's going to give us a real easy way to compute x bar of t. So the reason that we can do this is because the state of some linear time invariant system is not unique. If the state were unique, then there would be no such state x bar that we could use. But state is not unique. We can choose the state such that all of the pieces of the system that have memory are accurately described. And so there's more than one way to do that. You just end up with a different y equals something besides c times x bar. So we're going to create some thing called c bar times x bar to give us our output y back. So we'll see how that works out mathematically in a few minutes. It's just important to remember that the state of the system is not unique, so I can define my state such that a bar is diagonal. So if we have this magical matrix P, it'll have elements that look like this, that we multiply each of our x1, x2, all the way to x to the n. We'll pre-multiply x times P to get our new state x bar. All right. So now if we look at one of these values, xi bar, it equals pi1 times x plus times x1 plus pi2 times x2 plus all the way to pin times xn. So those are the n values of x, and each of these p values represents one row in the matrix, one element of a row of the matrix to calculate xi bar. So each xi bar is a linear combination of the terms x1 to xn. So each single element of the new state is a linear combination of all the elements of the old state. Likewise, we could define some matrix Q, which is equal to P inverse, and therefore we can write that Q times x bar is equal to Q times P times x, but since Q is equal to P inverse, this tells us that we can recover x by pre-multiplying x bar times Q. So this gives us the same thing. Each xj, each of our original states, is a linear combination of the x bar states. And it's for this reason that we know that we can move back and forth between these two definitions of state and things will work, because we're talking about just creating a linear combination of other bits of another matrix of this vector to create our own vector. So because it's a linear combination of pieces, that's why this is an equivalent representation of the state. So we can recover x if we have x bar. Therefore, in a way, we could recover x of t if we were able to calculate x bar of t. So because state is not unique, we can define a state update equation and an output equation to give us back y based on the same input u. We're just going to have the definition of time varying state be different. So b has to change to b bar, a has to change to a bar, and c has to change to c bar. So we can define these as x bar equals p times x. So therefore we can show by doing some pre-multiplication of our original state, or of our updated state equations and output equations. So we're going to pre-multiply both sides by p inverse. And so now p inverse times a bar times x bar plus p inverse times b bar times u. This is the same as p inverse times a bar times p times x, because x bar was equal to p times x, so we substitute p times x for x bar here. And so we can see that we actually get back, since p inverse times b bar, that's because we defined b bar, or we can define b to be p inverse times b bar. And so we can see that we recover x dot equals ax plus bu. So the a becomes equivalent to p inverse times a bar times p. So this is important. This is equivalent to a, and this is equivalent to b. So a is equal to p inverse times a bar times p, or we can actually just produce a bar by pre-multiplying a by p and then multiplying by p inverse. So if we just had this magical matrix P, then we could produce a bar and then calculate e to the a bar t super fast. And since b equals p inverse times b bar is equal to p times b, because we pre-multiply both sides by p. pb equals p times p inverse times b bar, so that just gives you the identity matrix b bar times b bar. So if y is equal to c times x, then we can substitute x bar is equal to p times x times c bar, because we defined that c bar has to exist. So c then is equal to c bar times p, or therefore c times p inverse is equal to c bar. There's just a little bit of matrix math you have to do here by adding the p inverse here and here. Okay, so now that we have the idea of how to get a bar, all we have to do is come up with our magical matrix P, such that a bar is diagonal. So how would we do such a thing? Well, first of all, if we could do this, we would get x bar of t, which is the solution to x bar dot equals a bar x bar plus b bar times u. Then we would be able to calculate x bar of t based on e to the ax bar, or e to the a bar t, times x0. And we again would just calculate y of t based on the fact that we had x of t and c bar. So again, how can we design P? In what way will P give us a diagonal matrix for a bar? So let's look back at what you've probably forgotten about eigenvalues and eigenvectors. So an eigenvalue, lambda, which is in the complex numbers, satisfies this equation. So lambda times e is equal to a times e. So lambda is an eigenvalue of a. And so if we multiply lambda times an eigenvector, and it equals a times the same eigenvector, then e is called an eigenvector and lambda is called an eigenvalue. So the vector e is called the eigenvector and it's associated with lambda. So for example, depending on the size of your matrix A, you'll have as many as n unique eigenvalues and eigenvectors. So, we're going to calculate the eigenvalues and eigenvectors of A to produce P. And I'll show you in a minute that if we use eigenvectors and eigenvalues to produce P, then we will definitely get a diagonal matrix if P is invertible. Let's see how to do this. So again, A is an n by n matrix, and it has n distinct eigenvectors, e1, e2, all the way to en. So I'm going to choose my matrix P to be made up of columns where each column is an eigenvector, e1, e2, all the way to en. So I'm going to create P inverse based on the columns of the eigenvectors. So how did I decide that I was going to do this? Well, somebody else decided this years ago and showed that this is a good method. But I'll show you why this is a good method in a minute. So once we have P inverse, we can invert P inverse to get P, and then compute A bar as P times A times P inverse. So let's assume for a minute that we know how to compute P. So P inverse pre-multiplied by both sides, so that gives us P inverse times A bar is equal to P inverse times P times A times P inverse. As you can see, some of these pieces go away. So P inverse times A bar is equal to A times P inverse. And I'll go ahead and just list out P inverse here, just as we defined it up above. So it's just a bunch of columns, and each column is an eigenvector. And I've pre-multiplied that by A. So in essence, I can actually go ahead and multiply each column by A, which is what I would be doing anyway. So AE1, AE2, all the way to AEN. But just a few seconds ago, I showed you that lambda 1 times E1 is equal to A times E1. These are the eigenvectors of eigenvalues of A. So I can take everywhere where I see AE1 here and replace it with lambda 1 E1 because of the fact that I created P based on eigenvectors. So lambda 1, lambda 2, all the way up to lambda n. So even though it isn't clear perhaps at first, this means that I can write my matrix E1, E2, all the way to En, and then multiply that matrix times a matrix A bar, which is a diagonal matrix of my eigenvalues. So take a minute to look at this if it doesn't make sense to you, and then you can look at it carefully to see that I am in fact multiplying lambda 1 by all the terms in E1, etc., to produce the first column, then the second column, all the way to the nth column. But this is what's really important. Here I have P inverse times A bar is equal to A times P inverse. So I've showed you how to create A bar. A bar is a diagonal matrix made up of the eigenvalues. And the eigenvalues are easy to compute. So P inverse is made up of my eigenvectors, and A bar is made up of my eigenvalues. And I can take these two matrices, A bar and P inverse, and tell you what y of t is going to be, because e to the A bar is really easy to compute. So the equivalent state space models for y of t, since we have x dot equals ax plus bu, y equals cx, so x bar dot equals a bar x bar plus b bar times u, and y equals c bar times x. So these are our two equivalent state space models, and we know how to create P inverse, and because we have calculators we can create P from P inverse, and we have A bar, which we create from the eigenvalues. So here x bar is equal to P times x, A bar is PA P inverse, B bar equals P times B, and C bar equals C times P inverse. So this, the top, gives us a difficult to calculate e to the at. The bottom alternative representation, e to the a bar t, is really easy to compute. And so when you can write where a bar is a diagonal matrix, this gives you modal diagonal form. And it's made possible by the fact that we can create P inverse from the eigenvectors and a bar from the eigenvalues. So if you want to determine the modes of the system, in fact, you don't even need to calculate P inverse. You can just look at the eigenvalues to find out what the modes of the system are going to be, which will tell you about e to the a bar times t.